Um, he is a very well-known mathematician in the Hopf algebra world. He obtained his PhD in 1999, and since then he has worked as a visiting scholar, visiting assistant professor at many universities around the world. And currently he is an associate professor at Memorial University of Newfoundland. His research interests include Hopf algebras, tensor categories, Hochschild cohomology, and related topics. He is the author of over a dozen scientific publications and 3 research monographs. And he's here to talk to us about Hopf algebras, history, achievements, and problems. So, Yorck, the public is all yours.
Thank you very much, Alberto. Okay, so let's see, here we go. Everybody can see this, yeah? Please tell me if there are technical problems. Yeah, Alberto, everything is fine? Okay, so I will briefly give you an overview first about what I'm going to talk about. So I will start with the definition of a Hopf algebra, and then I will discuss the historical development of the theory. I will briefly mention quantum groups and pointed Hopf algebras, to which in particular a great contribution is coming from South America. And then I will talk a little bit more about my own research area, which is more on the semi-simple Hopf algebra side. So, and at the end of the talk, I will discuss some open questions. So let's start with what is a Hopf algebra. And there is a non-rigorous but very brief and one-sentence definition. A Hopf algebra is an algebra for which you can form the tensor product of 2 representations. And what we will do now is we will explain what this sentence really means. And then secondly, we will make this definition rigorous. And the first thing that I want to do is I want to explain why it is in general not possible to form the tensor product of 2 representations of an algebra. So let's see how this works. So you don't have to know too much for the, but you have to know what a group is. So, and a representation is nothing but a group homomorphism from G to the general linear group of vector space V. That's a representation. And you can form the tensor product of 2 group representations, always. And if you have a second such representation, here denoted by rho prime, then you can map the group element G to just rho G tensor rho prime G. And this is an homomorphism of the, or an element of the general linear group of this, of the tensor product V tensor W. And this is, as you can easily check, again, a group homomorphism. So this is again a representation. Let's compare the situation with the representation of algebras. So if A is an algebra over a field K, and in the following, we very often will encounter vector spaces, and they will always be defined over this once and forever chosen base field K. Then a representation of A is nothing but an algebra homomorphism this time to the endomorphism algebra of a vector space V. And now let's suppose that we do the same thing and follow the same recipe that we have just seen for a group. So we take a second representation, taking values in the endomorphisms of another vector space W, and then the map that maps A to rho of A tensor rho prime of A. This is, although it is the same recipe that we have used for groups, is not an algebra homomorphism. And what is the reason for that? The reason for that is that this expression here is not linear in A, it is quadratic in A. In other words, if you multiply A on the left-hand side by 5, then this expression here on the right-hand side gets multiplied by 5 here, and by multiplied by 5 here, you can take both 5s out. So the expression in its entirety is multiplied by 25 and not by 5 as it should be. The expression is quadratic in A and not linear. So therefore, this is not an algebra homomorphism. It's also not additive for similar reasons. So in order to so for general algebra, you can not form the tensor representations in this way. What you rather need for an algebra is an additional structure element, and this structure element is called the coproduct. So the coproduct is an algebra homomorphism from A to A tensor A, whereas when I write here A tensor A and say this is an algebra homomorphism, it is understood that A tensor A carries the so-called canonical algebra structure where the tensor factors are being multiplied component-wise. Yeah, so this is how the algebra structure is there. And once I have this algebra, such an algebra homomorphism, I can indeed form the tensor product of two representations, namely in the following, not following the recipe as before, but rather I first apply the coproduct, then I'm in A tensor A, and then I form rho of A tensor rho prime of A, then I'm in end V tensor and W, which kind of maps canonically into this space end V tensor W here. So this is now linear in A, as you see, whereas the previous expression was quadratic in A. Now, so this is a structure element that we need in order to form this, but we want that this structure element, this coproduct, satisfies certain properties. And because we want to ensure that this the tensor product of two representations is taken in a nice way. And in particular, there is this canonical isomorphism between the two ways how to bracket a product of three representations. And this is, of course, a vector space isomorphism, just sort of moving the parentheses. But we want that this is alinear, so a modular homomorphism or a homomorphism of representations. And this means that we require that the coproduct is co-associative. So this is the corresponding equation we have over here. So we take, if you look at this bracketing, then the corresponding action that you need over here is has the coproduct on the left, whereas if you look at the bracketing over here, the corresponding coproduct that you need in order to act on this space is this form over here. So these are the two ways, and they should be equal in order for this canonical isomorphism to be alinear. So this is like coming from as kind of associative law for representations requires that our coproduct is co-associative. Now, there is next we discuss the so-called group algebra, and it will become apparent why, because at the end of this discussion here, you will have the first example of a Hopf algebra, and this is this group algebra. So let's again start with a group G. And then the group algebra of G is just the vector space, the so-called free vector space over G. So it's a vector space which has this given set as a basis. There is a general construction that accomplishes this. So this is what the group algebra. So the general element looks like this. It's a linear combination of the group elements. So the G are the basis. The coefficients alpha G come from K. It's supposed to be a finite sum. So this means only finitely many of these alpha G's can be non-zero. This is the structure as a vector space, but we want to turn this into an algebra, as the name suggests. Now, on this situation, you know already how to multiply basis elements, because you know how to multiply two group elements, and they are the basis elements of this algebra. Sorry. And now we just extend this multiplication that is already given bilinearly. So if you have two elements, one with coefficients alpha and the second one with coefficients beta, you just take these two sums out and you take the coefficients out, and then you multiply. So this is what you do here. This is a double sum in the beginning, and you have here alpha G times beta H, and then you have here the product of the basis element. But as I said before, you know already how this is being defined, or is supposed to be defined. So this is the algebra structure. And now it turns out that the representations of a group in the way that I introduced on the first slide, and the representations of an algebra are in bijective correspondence in this situation, because if you have a representation of G of the group, you can just extend it linearly to an algebra homomorphism from the group algebra, because on the basis element you already know how this is defined. And conversely, the converse is even easier. If you have an algebra homomorphism from which is defined on the group algebra, then you just restrict to the basis elements the group G, and then you get a group homomorphism, and the endomorphisms that come out are automatically invertible, because the corresponding inverse that you need is the image of rho, the image under rho of the inverse group element. So this works automatically. So in other words, this means for the group algebra, I can form the tensor product of two representations, because I know I can form the tensor product of two representations of a group. So if my general philosophy is correct, this would mean that my group algebra must have a coproduct, okay? Because the coproduct is what I need to turn the representations of the two the tensor product of two representations into a representation again. Let's discuss how this coproduct actually looks. So the corresponding coproduct must be an algebra homomorphism from the group algebra to the tensor product of the group algebra with itself. And on basis elements, I want to copy how I defined the tensor product of two group representations. So in other words, on basis elements, I want that delta of G is G tensor G, because this reproduces, sorry, this was wrong. I must not touch the scroll, the mouse, the scroll wheel. So on this definition reproduces on the basis elements the recipe for forming tensor product of group representations that I had on the first slide. And on general elements, this has to be an algebra homomorphism. So what I have to, it has to be defined like this. There is no other way, because the map that I use for the definition, it has to be linear, so it has to pass through the sum. The coefficients alpha G from the base field must be able to come out. And then on the basis elements, I have to apply this definition. So this is in general how this thing has to look. And this also works. Okay, so this is this. Now for groups, there are two special representations. And if we go now over this slide, keep in mind that we had already a kind of associative law for representations, which led us to the co-associativity for the corresponding coproduct. So we have a group, and then there's the so-called trivial representation, which just maps every group element to the 1 times 1 matrix with unique entry 1. Okay, so this is, and there is the distinction between a 1 times 1 matrix and an element in the field is not so big, so we kind of forget these parentheses. So this is basically saying I map every group element to 1 in the base field. Yeah, so this is basically the situation there. And this representation behaves like a unit element for representations, because there is a canonical isomorphism between the vector space V and the tensor product K tensor V. This is of course in the finite dimensional case a vector space of the same dimension, and there's a canonical isomorphism always. And also the same holds for the right hand side. This isomorphism is always there, but if I think of the base field K as endowed with the trivial representation, then also this becomes a modular homomorphism, KG linear, or we also say G equivariant. So this is compatible with the G actions on both sides, yeah, for the trivial representation. Now, okay, so we understand now that there is an associative law for representations, and there is also a unit element for representations, which I've just discussed. So this, following the group axioms, you would now ask, is there for every representation an inverse? Now, this cannot happen, of course. For example, if my representation has dimension 5, then I cannot tensor it with anything else to get a one-dimensional representation out of it, which would be the trivial representation, because all tensor products must have a dimension larger than 5 that I tensor with this given representation. But there is a substitute for this, namely the so-called dual representation. Thus, I denote it by rho star, and it takes values in the dual vector space, endomorphisms of the dual vector space, being denoted by v star. And what does it do? Well, I map first. I take the inverse element, I map it to an endomorphism of v, and then I take the transposed map. This is the transposition is, if you think of matrices, it's transposition, and in the abstract setting, I think you know how to do this. So, and the point is here, there is a canonical evaluation map. So if you have an element from the dual space and an element from the vector space, then you can evaluate the linear form on a vector, and then you get a number out. So there's a canonical map from v star tensor v to v. This is not an isomorphism, of course, but it's at least a morphism, and this canonical map becomes, as we will now see, kg linear with respect to this representations. So if I first take a linear form phi from v star and a vector v from v, little v from big V, and then act on it with the recipe that I had explained on the first slide, I have to do this component wise. So the dual representation acts on this, and then the given representation acts on v. And then I apply this evaluation map, so I evaluate these guys on each other. Because rho star is defined via the transposition, in fact, if I evaluate, this here moves into the argument because of this transposition, and then the corresponding element over here comes inside. And now, because of the representation property, you see that this term cancels against this term over here. And the result is these two terms cancel out, and I have phi of v. But phi of v is the same as if I would have first evaluated phi on v. This is the result of the evaluation map, and then acted trivially in the trivial representation, because the trivial representation does nothing. So this computation shows that the evaluation map is kg linear. It's not an isomorphism, but it's a canonical map. So this is kind of the substitute for the inverse, so to speak. Okay, and now this is being reflected into special morphisms, which I have on the group algebra. First of all, this map epsilon that we saw over here, this map from G to end K, extends linearly to the whole group algebra. So it's given on basis elements already, and I just extend it linearly. And what is the property then? The property that it has, if I take delta of G, which is G tensor G, and then apply epsilon, this here becomes 1 tensor G, this one being the one in the base field, and the same holds on the other side. And these are exactly the properties, if you look at this, these are exactly the properties that were necessary to make this isomorphism here G equivariant or kg linear, which is the same thing. So this is the so-called co-unit in this setting. And then there's also a second morphism, the so-called antipode, which is defined on the basis elements by just mapping every group element to its inverse, and then extending linearly to its, so it does not map an arbitrary element to its inverse, because an arbitrary element is not even invertible, but it maps the basis elements to the inverses and then extends this linearly. And this now satisfies the following two equations. If I first apply the coproduct, get G tensor G, and then apply the antipode on the left tensor factor, mapping this to G inverse tensor G, and then multiply the results together. The M is the multiplication map. Then I get this result over here. The antipode maps this G tensor G, this maps to G inverse. And then, of course, if you multiply them together, you get here 1. And it's important to epsilon of G is 1. Yeah, and the ones differ here. This is the one in the group. This here is the one in the base. So this is the one in the base field. This is one in the base field. This is one in the group. And so epsilon of G is 1 in the base field. But it doesn't change. But it's important to, of course, the one in the base field can be left out. This is what this equation says, but it's nonetheless important to have it, as we will understand in a second. And you can, of course, play the game on the other side and get the similar equation that you have over here. And if you think about this and go back a little bit, let's go back a little bit, but slowly. So then this property, the equation that I've just derived for you in terms of the antipode, is exactly what made this computation here at the bottom of the previous slide work. So you have here, this is exactly what you need, is G inverse G. So this is the multiplication followed by the antipode. Here's the antipode, and before there was the coproduct. I hope you see this. It's basically the same equation is which is necessary. Okay. And now, after all this introduction, we can define rigorously what a Hopf algebra is, and we are just copying the properties that the group algebra has and make them axioms. Okay. So what is now a Hopf algebra? So this is now the rigorous definition that we reach after the non-rigorous definition on the first slide. A Hopf algebra is an algebra, H, together with the co-associative algebra homomorphism, the so-called coproduct, which goes from H to H tensor H. It also has an algebra homomorphism from H to K, the base field, called the counit, which satisfies this equation over here, these two equations. And then finally, so I hope that you recognize these equations. We also had them on the previous slide. These are these two equations over here, which were written out for group elements. And then the last condition is, so we have this counit, and then we have a linear map, S from H to H, called the antipode, which satisfies these two equations over here. Multiplication, S tensor identity, coproduct of H is epsilon H tensor 1, and also on with the antipode on the other side. And I hope you recognize this equation too. Please observe that I put an epsilon H in here, on which I will comment in a second. You will recognize that this is exactly the equation that I derived here. So this is what I derived on the previous slide. Okay. So let's go back to this. So these are the equations. So why is it important to have the epsilon of H over here? If I would leave it out, the equation would not make sense, because what I need to make sure is, if I write down an axiom, if the left-hand side is linear in H, I need to make sure that the right-hand side is linear in H too. Otherwise, these two things cannot be equal. And if I would leave this epsilon out, the corresponding expression would not be linear in H anymore. Okay, yeah. So this cannot be equal to 1. This does not make any sense, because if you multiply it by 5, the H by 5, you can take it out here, and then the equation would say 5 is equal to 1, which doesn't make any sense. So both expressions have to be linear in H, and this is the role of this epsilon. Okay. All right, so far so good. Now you know what a Hopf algebra is. And so this finishes the first part of the talk. And what I want to discuss now is I want to give a little historical account how this notion came about. So there were two main sources for the theory. The first was the first source was algebraic topology, and then the second source were linear algebraic groups. And I will discuss both of them briefly now. So in algebraic topology, this is where really the name comes from. Heinz Hopf in 1941 investigated the singular cohomology ring of a group. When I write here singular, I mean that he investigated it topologically. I'll write this to distinguish it from group cohomology. This is not what I mean here, yeah? It's the group as a topological space. And then he saw that the product on the Lie group leads to a corresponding coproduct on the cohomology ring. Yeah, so this was the cohomology ring of a Lie group has an additional structure element over the general cohomology ring, namely a coproduct. And then Armand Borel elaborated on the work of Hopf and uses for the first, the article is written in French, he uses the first time the word Hopf algebra, or at least its French equivalent, algebra de Hopf. And this was a long line of development, and there was a paper by John Milner and John Moore on the structure of Hopf algebras, published in the Annals of Mathematics in 1965. And there's one thing that should be emphasized here. The Hopf algebras that we encounter here are not 100% precisely Hopf algebras in the sense that I have discussed before. Rather, in the new terminology, they are Jette-Drinfeld Hopf algebras over the group with two elements. So they carry so they are graded with a group of two elements, and if you form the tensor product, there is a sign involved in case that you interchange tensor factors which are both of odd degree, odd elements and even elements. So this is a feature that I did not have before, but I will not go into this into great detail now. Rather, I will define the second source for Hopf algebras, linear algebraic groups. So what is an affine group stream? And I will do this by an example. So suppose that we have a commutative algebra over a field K. And once we have this, we can form the 2 times 2 matrix with determinant 1 and entries in this algebra R. So here, in contrast to previously, the matrix does not have entries in the base field, but rather it has entries in R. The algebra that I'm looking at, A, B, C, D, and R, and I require that the determinant of this whole thing is equal to 1. So this means that the matrix is automatically invertible. And the point of view here now is this defines a functor. This was the initial insight between the scheme theoretic viewpoint. This defines a functor from the category, usually one requires here that all the algebras are finitely generated, from the category of, say, finitely generated commutative K algebras to groups. So in other words, this depends functorially on this R, because if you have an algebra homomorphism to another commutative algebra, you can apply this algebra homomorphism to each of the components and get a corresponding entry in SL2 of this new algebra. Yeah. So it depends functorially on this, and it turns out that this functor is representable. And the representing object is the K algebra in the commuting generators U, X, Y, and Z, which roughly corresponds, as you will see, to A, B, C, D. So I started with U because, well, I could start with X too, but there's this problem that the alphabet ends at Z, yeah? And the defining relation is basically the determinant relation. So there's one defining relation, AZ minus XY. Y is equal to 1. And then if you look at this, then an element in SL2R is the same as an algebra homomorphism from this new algebra H to this commutative algebra R, and it's defined on the generators by mapping U to A, X to B, Y to Z, and Y to C, I wanted to say, and Z to D. And you see then this defining relation then means that the implies that the determinant of the outcome matrix is really in SL2R. The determinant is 1. And now the product of two matrices corresponds to the so-called convolution product of the corresponding algebra homomorphisms. This means this. So if my first matrix corresponds to an algebra homomorphism F, and my second matrix corresponds to an algebra homomorphism G, then the matrix product corresponds to this convolution product F star G, which is defined as, first apply a certain coproduct, which I still need to tell you about. This is coming below. Then I apply the tensor product F tensor G, and then I multiply these together in the algebra R. So I have to specify what this delta is. Mu R is the product in R, and the coproduct goes from H to H tensor H, and it's defined like this. Delta of U is U tensor U. I will motivate this in a second, but think of matrix multiplication. U is roughly A, so we have here A and A. So I will explain this in a second. So, and then we have so this is basically the second component in the matrix multiplication. I will explain this on a sheet. Here we go. So this is what we have. So this is what we get because we can multiply matrices in SL2R. This means that, and this depends functorially on R, this means for the representing object that it is a Hopf algebra with this coproduct delta. Let me briefly explain this, how these formulas come about in greater detail. Can you see this, Alberto, what I'm writing?
Yes, I can see.
Okay, so let's briefly think how two matrices are multiplied. So we have A, B, C, D. And then we have here, say, A prime, B prime, C prime, D prime. Yeah. Then, of course, everybody can form the matrix product. And we have here A prime plus BC prime, right? And I don't go over the other, everybody can do this. So, okay, so then let's say this, the first thing corresponds to an algebra homomorphism. This would be F of U, F of X, F of Y, and F of Z. And this here would be corresponding to G, G of U, G of X, G of Y, and G of Z. Then the corresponding formula here would be F of U, G of U, plus, this is this entry here, F of X, G of Y, right? And then three other entries. And this here is now exactly the convolution product as you will, so this is mu R of F tensor G applied to U tensor U plus X tensor Y. See this? You apply this component wise, and then you multiply the result together, and there are 4 other entries. And now if you look at this, keep in mind U tensor U, this expression you should keep in mind here, this U tensor U and X tensor Y, and then you compare this to what we had over here. So can you see this, Alberto? This is U tensor U plus Y tensor, yeah?
Yeah.
Okay, so this is how these come about, and the other formulas come about by looking at the other expressions for matrix multiplication. So this is how this how these things go together. Okay. So the so this is how the Hopf algebras come about here. If you have a functor from the category of finitely generated R algebras to the category of groups, and this functor is representable, then the group structure is reflected in the existence of a coproduct in the representing object, turning this into a Hopf algebra. So this is the second source for Hopf algebras. And following work of Dieudonné and Cartier, this viewpoint was then developed by Hochschild and Costand. And after out of this came, after some work, there was in 1969 the first book on the entire subject appeared, which was by Moss Sweedler. The book is just called Hopf algebras and was published by W.A. Benjamin in 1969. And since then, you can say the theory existed on its own right and has been, Hopf algebras have been investigated on their own right and have, I can say, been found to be connected to practically everything in mathematics, in particular mathematical physics, all different branches of physics, algebraic combinatorics. There are many, many, many connections of this theory to other branches of mathematics, which I will not discuss in this talk, maybe some other time. So let's briefly look at how from this point in time the theory developed further. So this was at that point relatively new, and so in 1975, Erwin Kaplansky gave a course on Hopf algebras at the University of Chicago, and he wrote a bunch of lecture notes for that, and these lecture notes have an appendix, and in this appendix he stated 10 conjectures on Hopf algebras, in particular about the semi-simple ones, which I will discuss in a second. And then results on these conjectures were approved by Richard Larson and David Radford in the 80s, and by other people too, I should say, not only by these two, but especially by these two people. And several of these conjectures are still open. That's quite remarkable. I will discuss this in the sequel. So, and then another important example, and so this was what was happening in the 70s and 80s, and then in the 90s, the deformations of the coordinate rings of linear algebraic groups like SL2R above that I've just described, deformations of these coordinate rings appeared. And there were also deformations of the universal enveloping algebras of the corresponding Lie algebras. So these were found, in particular in the work by Ludwig Fadeev, Nikolai Reshetkin, and Vladimir Drinfeld, in the St. Petersburg School of Ludwig Fadeev, which worked on integrable models in statistical mechanics and quantum field theory. And it was not so clear to them at the beginning how Hopf algebras came into play then. I think Drinfeld played a key role in clarifying that. And these provided new examples for Hopf algebras, the second kind of which, and I mean the universal enveloping algebras here, of the deformations, the second one kind of which is pointed. And this leads, of course, to the question how pointed Hopf algebras look in general. And there has been a lot of push in this direction, people from, in particular, coming from Argentina. Nicolas Andruszkiewicz and his student Ivan Angiolo played a key role, but also one German, actually the co-supervisor of my thesis, Hans-Jürgen Schneider in Munich. Okay, so this is was one kind of key points of the development, and another kind of another line of developments were the questions on semi-simple Hopf algebras, which is more my research area. And then, so let's first state, it's not completely obvious, but true, that the semi-simple Hopf algebra is automatically finite dimensional. And an element in a Hopf algebra in general is called the left integral if it reproduces itself under left multiplication. Now, it cannot reproduce itself, because if it can only, because of linearity requirements that I explained already before, it can only reproduce itself up to a factor. Because if you multiply the element by 5 times 1, it has to multiply itself by 5. So this is the best thing that can happen. It can reproduce itself up to a factor, and the factor is given by the by epsilon of h. Yeah, so this is the best thing that you can hope for. And if this equation here holds for all h and h, then we talk about a left integral. Such elements exist if and only if h is, well, 0 is always, 0, lambda equals 0 always satisfies this. But non-zero left integrals exist if and only if h is finite dimensional. If they exist, they are unique up to scalar multiples, that you can modify this here by that you can multiply lambda both, you can multiply both sides by 5, and then you get another integral lambda times 5. This is obvious. But this is also the only thing that you can do in this case. Yeah. They are unique up to scalar multiples. Let me give you one example, and we have discussed before the group algebra. So if we take a finite group and look at the corresponding group algebra, then this element here, the sum of all the group elements, this is an integral. Let's check why this is the case. It happens to be also a right integral. It's two-sided, but I won't discuss that. So let's briefly take this. Let's first take a group element. This is, of course, not the general case. We take an element, a basis element, an element from the group, and then we multiply these guys together. So then, of course, this can go through the sum because the operation is bilinear. And then you have here the product of the group elements, but this is a permutation of the, so this sum is just being summed over in a different order. So, and if you kind of rearrange the summands, then you see that this is equal to the original integral that you have over here. Oh, it's now knocking at my door, but I don't have time for that. This is really unfortunate. So we then have, so this is equal to, I have to go downstairs for a second. I don't know what's going on here. 1 second, yeah? Don't know what's happening. Nobody there. Okay. Sorry for that. So I've showed this. So if you have lambda of h times lambda, this reproduces itself basically. It's equal to lambda, and because we're in the group, epsilon of h is equal to 1. So I can put this epsilon in. But now that we have this, sorry. Now that we have this equation here, this is a linear equation. So this equation now, because I put this epsilon in, this depends linearly on the argument h. And so if I check this equation on basis element, it holds everywhere. Now there's a theorem that is used can be used to characterize semi-simple Hopf algebras. If I have a finite dimensional Hopf algebra, then I have just explained that there exists a non-zero left integral. And so the Maschke's theorem says H is semi-simple if and only if the co-unit takes a non-zero value on this left integral. Let's look at this. So this is called Maschke's theorem for Hopf algebras. You may know the Maschke's theorem for ordinary groups. And this is a special case because if G is a finite group and H is the corresponding group algebra, then epsilon of lambda, you remember that lambda was the sum of all the group elements, and epsilon maps every group element to 1 in the base field. So you have the sum of all the group elements, but for each summit is equal to 1 in the base field. So this is, of course, 1 plus 1 plus 1 is just the number of summits, and this is the order of the group, but understood as an element in the base field, which then means that the group algebra is semi-simple if this number of the summits, is non-zero as an element in the base field, which will happen if the characteristic does not divide the group order. And this is Maschke's theorem in the original setting for groups. This is the Hopf algebraic generalization. So this is an important fact. Let's talk about some known results for semi-simple Hopf algebras. So for a finite dimensional Hopf algebra over a field of characteristics 0, the following conditions are equivalent. First of all, H is semi-simple. Second, the dual Hopf algebra, the dual space in which the coproduct induces the product and the product induces the coproduct, is semi-simple. And then secondly, the square of the antipode is in involution. This is quite remarkable because if you think how we introduced the antipode, it was kind of like a generalized inverse. So you could expect that in principle the antipode is always an involution. The square of the antipode is always the identity, but this does not happen. In fact, in this sense that I've explained here, this characterizes the semi-simple case. So this result is due to Larsen and Redford in '88. And in positive characteristics, this is actually open. So it is an open question whether if the characteristic does not divide the dimension of a finite dimensional Hopf algebra, is it then true that these properties 1 and 2 are equivalent? This is an open question. This is one of the conjectures that is on Kaplansky's list in the appendix of his lecture notes in Chicago that I mentioned earlier. And there's another open problem, which I find particularly interesting, but it's not very easy, but highly relevant. So this is the 6th conjecture. So suppose that K is algebraically closed of characteristic 0, and that H is a semi-simple Hopf algebra. And then the question is, does the dimension of a simple module always divide the dimension of this Hopf algebra? Remember that this is the case for groups. So for group algebras, this is a theorem of Georg Frobenius. But one should say it's not clear whether this straightforward generalization of Frobenius' theorem is actually the right one, because there is a result for Hopf algebras that would imply for Frobenius' theorem for groups. So there is a generalization, but it's not this one. This is the so-called class equation by for Hopf algebras, a results complicated history by G.E. Kutch and Yongchang Zhu. I will not cover the history at this point. But the general question that, maybe the more very important question for semi-simple Hopf algebras is the following. Semi-simple Hopf algebras appear to come from finite groups, over, say, algebraically closed fields of characteristics 0 at least. And the evidence for this is as follows. If the dimension is prime, then the Hopf algebra is always a group algebra in the first place. This was Kaplansky's H conjecture, which was settled by Kutch and Zhu using the class equation that I just mentioned. If the dimension of the Hopf algebra is P times Q for distinct primes P and Q, then H or H star is a group algebra. And this was worked by several people in several papers. I contributed to this a little bit. But the main question is the following. Semi-simple Hopf algebras arise from finite groups via a number of constructions, such as Redford biproducts, extensions, and twisting. Twisting is here conjugation of the coproduct. The main question is the following. Is there a universal way how every semi-simple Hopf algebra can be constructed from finite groups in some way or the other? So this is basically and nobody has a really well, there are various ways how to make this question precise. I don't think that there is not even a perfect conjecture to make precise what this universal way would be. But maybe this is subject to discussion. But even if even if this universal way would be made precise at this point, this would be definitely so the first task is to make this universal way precise. And I think this is the pretty vague, but nonetheless pretty important question, which describes a basic problem with the theory at this point in time. All right, that's the end of my talk. Thank you very much for your attention.
Thank you very much, Yorck. So now we open for questions. I see Ronald has a question for you.
Let me see it, okay.
Sorry, I have no questions.
Okay. Well, I have a small question. I suppose that you're aware of the advances that Andruszkiewicz has been making in the classification of pointed Hopf algebras.
Yes,
so I don't know if you have a comment on that and the direction that he's taken with his group, and because apparently he knows that I saw him maybe a month ago for the Latin American Algebra Conference, and he knows that he can make a lot of progress. But I think, or that's at least what I understood from his talk, that there are major obstacles ahead. So I don't know if you have an opinion on that.
You can probably judge this better than I can. My personal opinion is that this work is absolutely great, what he has done there, and it is fantastic what they have accomplished. And in particular, what everybody must find impressive is how effectively he has built this group. I mean, how many people he has brought into the research area who really contributed greatly, and I've already mentioned Ivan Angiono, and so it's a tremendous achievement. The problems that when they go to they are doing several things. They are basically I think one can say where they are very far is in the program of describing pointed Hopf algebras, where the group algebra that is sitting at the bottom is abelian, and in the non-abelian case there is certainly still a lot to be done. But what they did in the abelian case is already super impressive, and what is coming now, I'm sure it will also be impressive. They will continue working on this, and how deep is, because it's not exactly my research area, I cannot say precisely how difficult the problems are. He can judge this certainly better than I can. This is sure. Yeah.
Okay. Well, thank you very much. I don't know if anyone has any comment, question, whatever. Well, apparently no. I also want to add that I was speaking to Lars today, and he sends regards. So he's saying,
regards back. Yeah. Okay.
Yeah, I think he's like 2 feet under snow already in Norway.
Oh, really?
Yeah, but he's saying hi.
Okay. Yeah. Please send him my regards back. Yeah.
And well, I also want to add that I'm really, really grateful to you for this talk. And our small group of study would love to have you at some point in the future
I
with
hope
us
that
again.
this will become possible. Yes, it would
Yeah.
be great to visit at some point.
Yeah.
Yeah, I think.
Perfect.
All right.
Well, so thank you very much. And thank you everybody for coming and joining us. Professor Yorck Sommerhäuser. Thank
Okay.
you.
Yeah. See you sometime in the future.
Definitely. Ciao.
Bye-bye.